Okay, so still on the same sheet. So we're at here effective interest rate. So that's what we're going to look at, and there's a new formula for that. So this formula is adapted specifically to convert interest rates to different forms. So the effective interest rate basically is like the annual, so this is effective interest. Basically, it converts interest rates to be an annual rate that we can compare to other interest rates. So it is the interest rate equivalent if there had been no compounding. So the letters are all the same. I is R over M, and this is just M because we're just converting an interest rate. It's not necessarily for a loan. So the example on the sheet, one of them says, would you rather earn 6% per year compounded semi-annually, or, so we're going to do comparison, I'll put it over here, 5.9% per year compounded daily. So they're close, and so this is getting interest every day, and this is only twice a year, so probably this one will end up being more because they're so close. It'll go a little bit above. You would make more money with this daily interest. So to do this, you just find the effective interest rate for both. So 1 plus 0.06, this is semi-annually, so that's 2 to the 2 minus 1. 0.06 divided by 2 plus 1 to the power 2. 0.0609, so 9.09% is the effective interest rate. And here, did the same thing. Now this is compounded daily, so that would be 365. .0607, so we'll put 77, we'll put 8. So 6.08. Okay, so I was wrong. It's not higher. It's a little bit lower. So if this is would you rather earn, so you're earning money, you want the higher interest rate. If you're earning. So here, 6% compounded semi-annually is higher. Now, if it was for a loan, you want the lower interest rate. So watch the question. If it's a loan, you want to pick the lower of the two, but if you're earning money like a savings account, then you want the higher. Question 2, find the nominal rate corresponding to an effective rate of, okay, so it's asking for the nominal rate. We didn't use that word before, corresponding to the effective rate, but the nominal rate is asking for that R. Is the nominal or annual rate before compounding, before dividing it. So the effective rate they're giving in the question is 0.1268, and it's compounded monthly. So if we write the formula out, we're going to find I and then use it to find R. So 0.1268, 1 plus I to the 12 minus 1. So here we would move the 1 over. And then to find the 12, you actually take the 12th root of each side. And then, let's just go up here, I will be the 12th root of 1.1268 minus 1. Okay, so the root button, so on the calculator, there's a y to the x button right here, and right above that it says x and then a radical sign, so that's the root. So you want to hit 12 and then second function. So that's what that looks like on the screen, the 12th root of 1.1268, and then subtract 1. So we'll get I equals 0.009998813. I'm just keeping lots of decimals here for a second because it's not I that we actually want. This rounds up. So usually with an interest rate, we're going to keep 4 decimals. 4 decimals will actually send this all the way back to 0.01, which is probably what the interest rate is. But we want R. So I is this. Oh, let's use the storage button because we're going to have to use those in the next section anyway. So let me just store this whole number. Store in A. Okay, so if I need that again, I can get it. Okay, it's in A. So here, I stored that in A. So I want to hit A, whatever number that is R over M, and M was 12. So to solve for R, we'll have 12 times A. And A was that number. So I could have left it on my screen, but I want to show you how to use the recall. So I want 12 times A. So 12 times recall, that's RCL, A. So it remembers that number. There it is. So R is 0.1199. We usually keep 4. That would round it up. So we would actually round it all the way up to here. So it would be 12%. Okay, so that's the effective interest rate. So now we're going to start the next page, which is saving. So this is part 2, effective plus annuities. Okay, so on the back of the sheet, we've got what are called ordinary annuities, and these are the formulas we're actually going to use for this whole sheet, along with the compound interest formula from the front page. So here we've got the 2 equations, and we've got what everything stands for. I'm going to write them out and just tell you the difference between them. Okay? So if you take a finance course, sometimes they look a little bit different. They've just arranged them differently, but they work the same. They might have slightly different letters in different books, but the equations are the same no matter what you're doing in finance. So these are the 2. Okay, so this S, we're going to say it stands for saving. It doesn't, but if you're saving, you're going to use this formula. So that's an easy way to remember. So if you're saving money, we're going to use this. It actually stands for sinking fund. Well, a sinking fund is when you have a goal in mind. So you're saving towards a certain amount. Say tuition or a down payment for a house. you know how much you want and how long you have to save it, and then you're going to find R. So R actually stands for rent. It's not rent in the way of an apartment, but what it is your payment. So it could be a monthly payment. Daily payment, weekly payment, annual payment, but basically you do it more than once. So with the compound interest that we saw before, that was just when you were saving, you put the money in once and then you let it sit and grow. That was the compound interest formula. So basically this is the idea. So you put an amount in here, we called it the principal, and then it grew to A, and that was A equals P, 1 plus I to the N. Okay, so it moved across N periods. And it grew, and it was an amount at the end. Okay, so that's compound interest. That's one initial deposit. Okay, now what we're doing here is we put in an amount R, and we do that regularly, say every month, every year, whatever the time period is. So we keep doing that, and then at the end, at the time of the last payment actually, the total at the time of the last payment. So there's actually no interest on that last payment. If you wanted your total, it calculates all of these over N time periods and also N deposits. So the number of deposits is the same as the number of times it's compounded. So here this was once, and this formula up here is when R is a regular payment, not just once, a whole bunch of times. So that's the difference. Now over here, this is more used for loans. P, we're going to say, stands for paying back. So there is a difference, so it could be a loan. And then that's called amortization, which we're going to do next time. Or it could be paying yourself. So what do I mean by paying yourself? Well, if you have a savings account with some amount in it, P is at the start, and then you withdraw, so you're subtracting all these payments. So this is taking money out. So like this is the principal, or how much you had in the account at the beginning, and this always reduces to 0 at the end. So using this formula, it's like if you had an amount, say you won the lottery, and you put that all in the bank, and you said, how much can I take out every month so that it lasts 20 years? So this would be 20 time periods times 12, and you withdraw until you have 0 at the end. Okay, so paying back is this one. It could be retirement. You have saved for retirement, and then you start withdrawing the money. So this S is called an increasing annuity because the money is growing. And P is called a decreasing annuity. So starts at P and ends at 0, and you have all these R's in between, withdraws. Here, this starts at, well, 0, but R. Okay, we'll say it starts at 0. You start with nothing, and you put all these deposits in. These ones are taking out, these ones are adding in, and then you end up with S at the end. That's the amount you have saved. Okay, so that's what the two formulas are. So we'll do a couple of these questions. The first one on the sheet says Jane decides to deposit payments of $1,000 at the end of each quarter year. So the 1,000 is payments. So payments at the end of each quarter year. So that's 4 times a year. So M would be 4 for 12 years at 6% compounded quarterly. I already wrote the quarterly down. How much money will she have? So she's depositing money. How much money will she have? So this is saving. She's saving money, so we're going to use this formula. To do this, we need I, which is R over M. And N, which is M times T. And our deposit is 1,000. That's the deposit she makes more than once. And you need to put this in a calculator all at once. So, to do that, what I usually do is this top first, okay, and I get that answer, and then hit divided by times this. So I just multiply this at the end. You can put it at the beginning, but you do need to have brackets if you do that. So what I usually do is get this number and hit equals. Okay. So 1 plus 0.015 is 1.015. So if you type it in that way, it's one number instead of with a plus sign, to the power 48. So I hit that y to the x, 48 equals minus 1, and that's the top. And then I hit divided by 0.015 and times 1,000. So you can plug it in a different way, but you really should practice that. So she has 69565.22. Okay, so an interesting question about this. So there's how much she has saved. So basically, here it is. She has 69565.22. At the end, she deposited $1,000. How many times did she deposit that? Well, she deposited it N times. So this happened 48 times she deposited that. So altogether, Jane deposited 1,000 times 48. So $48,000. And she earned 69565.22. So if we subtract those, the interest earned so the interest she earned would be that much. So to figure out the interest is, again, a little bit more complicated now, because you have to figure out, it's not just one deposit that you would subtract, it's however many times she put that in, you have to calculate. Okay, so number 2 says the parent wants to present a child with $20,000 when the child turns 18. So $20,000. The parent will make a deposit on each birthday starting when the child is born. So that's more than one deposit. It's going to be compounded annually, just once a year. They're only making a deposit once a year for 18 years. How large should the payments be if the account earns 6% compounded annually? And I already put the 1. Now this is the goal. So that's at the end. We want to save $20,000. So this is what's called a sinking fund. You are going to make deposits, 18 deposits, and you want it to be $20,000 at the end. So I is R divided by M, 0.06 divided by 1, so still 0.06. N is M times T, so 1 times 18 is 18. Oh, and S is 20,000. That's our goal. So 1 plus 0.06 to the power 18 minus 1 over 0.06. Okay, so now we need this whole number to be stored. So we're going to store this, let's say, in A. I always store in A. So you get that whole number, 1.06 to the power 18 minus 1 divided by 0.06. So that's this number. It's around 30. Okay. But we need it exact, so you cannot round it off, so we need to store that in A. Okay, so I stored it in A. I think, store A. Okay. And then, so what I've got now is an equation, 20,000 equals R times A, and I want to solve for R, so divide both sides by A. R equals 20,000 divided by A, and A is what's stored. So I would hit 20,000, oops, divided by, recall A. So 647.13. So payments on the child's birthday should be 647.13. And if they deposited that 18 times, it will grow to 20,000. So if we look at the interest again, because this is really a good thing to check. If you think about it, hopefully they've put in less money than they have at the end because they're saving. So it would grow, you'd earn interest on that. So they've done 647.13 how many times? They've deposited that 18 times. So let's just see what that works out to be. 647.13 times 18. So 11,000 is the deposits, total deposited. Through annual payments. Okay, so that's how much was deposited. And then 20,000 was the amount in the account at the end, was the amount saved. So if we wanted interest, the amount saved has to be bigger than the amount that you deposited, or else you did something wrong. And so that would be 8351.66. So that would be the amount earned in interest. Okay, number 3. Says Joe was offered a $2,400 starting bonus at his new job. Or the option of $100 each month for 2 years. If interest rates are 3%, compounded monthly. Which choice is better and by how much? Okay, so this is actually perfect because it's the difference between the formula, compound interest formula. This is $2,400 at once, and then it's going to earn interest. How long? 2 years? So 2 years, and it's compounded monthly. So, but it's once. We only got that amount once, and then it grew. So this is your principal, and it grows to A. It's like a lump sum, a one-time thing. So 2,400, 1 plus I, which is R over M. So 0.03 divided by 12 to the power N, which is M times T. You do need to remember these two formulas. I don't give those. So 12 times 2, 24. And so we can figure out what this lump sum one-time payment grew to. I just do this bracket first. So 2548.22. Okay, now over here, this is $100 per month for 2 years. So that actually will be $100 24 times. So it's the same amount, but it's gradual. So instead, you're given $100 and then $100 and $100, and that happens 24 times until you have an amount saved at the end. So this is going to be less because it starts with more. Right away here, you're earning the interest rate, 0.03 divided by 12. Like after month 1, if we take that monthly interest rate, so 0.0025, and multiply it by 2,400, after the, 2,400 times 0.03 divided by 12, $6. Okay, so I just multiplied that one rate. What I did was the 0.03 divided by 12 times 24, and that gave me 6. That is the interest added in month 1. Now, what's the interest added in month 1 here? Well, in month 1, we only have $100 instead of the 2,400. $0.25. So here we have 25 cents added on. Then you're going to add another 100, so it'll grow by 100 more, so then you'll have 100 and 125 cents, but then you'll get more interest. But here, this will already be 2,406, so then the next month it'll be more interest. So right away you're earning more. Here the interest starts small and then it grows bigger. So you're going to end up with less if you put the money in gradually rather than just putting it all in at once. So this is $100 is the payment, and is 24 times. Get this whole bracket and times it by 100. You can use your storage buttons to store parts, but you can't round off until the very end right here. So if you got it all at once, you'd have 2,548, and if you got it 100 at a time, you'd have 2,470. So the interest earned is 70.28, and the interest over here, 2,400 was the amount that we started with, so 148.22. So it's double. Or just about. The question said, which choice is better and by how much? So the 2,400 starting bonus is better by, and let's subtract these two. So this one is $77.94, larger than the other option. Okay, question 4. How much money must you deposit now at 5% compounded quarterly in order to be able to withdraw $1,000 at the end of each quarter year for 3 years? So here they're saying what? We want to start with an amount and then we withdraw all the way until it's at 0. So this is when you're sort of paying yourself back. So that's the other formula, the decreasing annuity, since it's getting smaller. And I would be 0.05 divided by 4. N is M times T, so 12. And we want to withdraw this every quarter year, so that's more than one time. Now here we didn't use this formula yet, but that's got a negative as the exponent. So you do have to put that as a negative. So here 1 minus 1.0125 to the power, so y to the x. So I didn't put this plus sign in because this is just 1.0125. Now when you do negative, you don't hit the minus sign, not right here, that won't work, that'll give you an error. You have to hit the sign on your calculator that has a plus minus, and that gives you a negative. So negative 12 divided by 0.0125 and times 1,000. So if we deposit 11,000 and then you withdraw $1,000 12 times, then it'll be down to 0. So the interest actually works the opposite way. So the question asks for this. But we're going to talk about the interest. So the withdrawal payments, withdrawn amount, was $1,000 12 times. So 12,000. So you withdrew more than you put in. Well, that makes sense because you put it in here and you don't withdraw the whole thing. So you do earn a little bit of interest. So interest is going up, but the total amount is going down because you're taking out more than the interest. So you withdrew 12,000 altogether and you put in the 11,000. So 920.69 is the interest you earned. All right, so if you were doing like a lottery, say you won $1 million and you wanted to withdraw just the interest, and so then it would never go down, your account would always have the same amount, you could figure that out too. Let's just do that as a little example. Say you had $1 million. and your interest rate was 3% compounded monthly, 0.0025. So this is monthly. And say you wanted to withdraw an amount monthly so that the account never changed, then 1 million times 0.0025 is $2,500. So that's the interest that would be added on. And if you only withdrew that and nothing more, then it would stay at $1 million, and every month you could withdraw $2,500. Now, if you started withdrawing more, then it would start going down, and eventually it would go to zero because you're withdrawing more than the interest. So that's just an interesting question. If you live on the interest of some amount, then your account just always stays the same, and you'll always have that money. All right, so one more question. It says, I started a savings plan where I deposit $200 at the end of each month into a savings account. So this is a monthly payment. So let's put M as 12. Earning 3% compounded monthly. I already put that part for 2 years. After the 2 years, okay, so let's draw a number line. So here's time 0 and time 2. And here we're putting in $200. That's a whole bunch of times, okay? 2 years times 12, actually. 2 times 12, 24 times. Okay, and then it says after the 2 years, I'll start depositing $400. Same interest rate. Yeah, it doesn't change the interest rate. You could change the interest rate, but it doesn't say. At the end of each month for 3 years. So this will be time 5 at the end, but T is 3, and it's 3 times 12, so 36 times that you'll do that. And then it's going to ask for the balance. So Part A actually asks for the balance right here. So the balance at the end of 2 years, so we're saving. R is 200. I is 0.03 divided by 12. So 1 plus 0.0025 to the power 24. That's the 2 years. Okay. So right here, if you've looked at the balance before you started depositing the $400, this would be the balance. And then Part B says, how much interest in the 2 years? So the deposits were what? $200, 24 times. For $4,800, and the total earned was $49.40.56. So $140.56 is the interest earned. All right, your deposits are less because you earned money, and this is the amount that's in the account. And Part C, how much at the end of 5 years? Okay, so this is where we really need this amount whether it asked for it or not, because what happens if you look up at the number line here, this amount is sort of two separate things happening. So now we're going to put 400 in 36 times, and we can figure out that amount from here to there. And that'll give us an amount right here at the end. This, meanwhile, this sits in the bank as a lump sum for 36 periods. Okay, so you do them separately. You don't add payments on to a previous balance. The payments, you kind of think of it as starting at zero, and this one is earning interest at the same time. So there's two parts to this. There is the lump sum that starts at $49.40.56 and is going to grow to be an accumulated value. So this is A equals P, 1 plus I to the N. So A is 49.40.56. What was the interest rate? 0.0025 to the power N. So it's going to sit in the bank for that 36 periods. It was 49.40.56, and it's going to sit in the bank and be an amount at the end. Okay. Meanwhile, the payments are $400. I is 0.0025, same bank account. N is 36, it's for 3 years, and we're saving. So 400, I'm just looking up here at the formula, 1.0025 to the power 36, that can't be right. Oh, I just put the decimal in the wrong place. 15048.22. Okay, so this was from our lump sum, and this was from our payments. And so if we add those together, we'll have our total. So 20,451.45. And that would be the answer to the question. Okay, so here's the homework. So here is a would you rather pay, that's a comparison of interest rates. So that's an effective interest rate. There's simple interest. It says simple interest rate in it, so that's obvious what formula to use. 3, how much interest is paid on a loan of $1 million at 5% compounded semi-annually for 15 years? So this is not mentioning any kind of payments, so this would just be a lump sum. You're looking for the interest in the end. 4, how much must be placed in a savings account each quarter year if you wish to accumulate $6,000 in 5 years at 1.4% compounded quarterly? So this is a savings account, but we're going to do it each quarter year. So this, it happens more than once, so then you're looking at the savings formula. 5, what is the principal of a loan that was taken for 10 years at 12% compounded monthly with payments? So this is a loan, so this would be, oops, P equals R. So it's a loan, but it's talking about monthly payments. So then we would plug it into that formula. We're going to do more on loans next class. Herb is saving money. He deposits a lump sum of $500 into a bank account. After 1 year, he deposits $50 per month into the account for the next 5 years. So after the 6 years, the 1 month of just the $500 and then the 5 years of that, he decides to stop and leaves the money there for 4 more years. How much is in the account after 10 years? How much did he earn in interest? So that's similar to this question. I would just draw a timeline. I'm going to draw one for you to help you out. So, at the start, he deposits $500, and that sits for 1 year. Compounded monthly, so that's actually 12 times 1 periods. But it sits there. There's no further deposits. So this is a lump sum. You figure it out this way. Now that gets you to this point. Okay, let's put it in a different color. What happens next? So then at that point, you start making payments, or he starts making payments, $50 per month. So that's an R value. And he does that R a whole bunch of times, 5 years, every month, so 60 times. So all of those are going to accumulate to an S, and that will be right here. And then so at the end, he stops making payments. So right here, he stops putting $50 a month in and leaves the money there for 4 years. So one thing you have to do is make sure this money moves up to here. So whatever you have at this point, the total, then becomes the principal. So the total from here, whatever you get as your total for that 500, it grew to some amount over 500. You put it in here, and then it grows further to a new A. And this new A plus this new S, if we added those together, then are going to sit in the bank for how long did he say? 4 more years. So 4 times 12 periods is 48 periods. So again, this total would be a lump sum. They're not adding anything to it. So you'd use that total as your principal, and you'd find your new A at the end. Okay, so let's recap. 500 is a lump sum. There's no payments, so you use the compound interest formula. That only brings it to here. We do want to bring it all the way to this point in time, so it still sits in the bank, not just for the 1 year, but it actually sits in the bank right to here, which makes me think of another way you could do this, even easier. So that 500 is going to sit in the bank for the whole period, 10 years. You could figure it out as a lump sum that way. That's so much easier. If you did it both ways, you could get the same answer. Would be a good thing to try. What happens with this $50 is that happened here for 60 periods. And that was 50, 1 plus I to the n minus 1 over I. So that S is right here, but then that sits in the bank for 4 years. So you do need to do this as 2 separate calculations. You'd get this S, and then you would put it in here as your principal that sits for 4 years. So N would be 4 times 12. Okay, and that will bring the money both to these points. So I'm going to get you to try that. I walked you through it. That's the homework, so you should be able to complete all of that homework. And then we'll see you on Tuesday.